In the previous lecture, we introduced the concept of rolling. We looked at how to combine rotational motion and translational motion together. And today we're going to be, inshallah, building up on that. So, let's take a look first at forces and kinetic energy of rolling. In your book, this is all part of 11.2 and 11.1, which is rolling and angular momentum. I am breaking it down to multiple pieces because I think it's easier to follow when you're going through multiple pieces rather than one go. So first thing first, we have touched on this in the previous lecture, the kinetic energy of rolling. Now, if we take this wheel that we have been focusing on so intently for the past lecture, and we trace its motion, okay, along, if we choose point P as the point of rotation, okay. Now, there's a ground there, so it's not allowed to do this, but if the ground was not there and it was just allowed to rotate, this is what it would do, right? It would just go in a full circle. Now, its kinetic energy of rotation would be half I omega squared. And I denoted by IP to mean that it is I, the moment of inertia at point P. So half I omega squared. Okay? Now, if I expand this further, what is IP? IP is my I center of mass plus mr squared, according to our rule that I at any point x is equal to I com plus mh squared. Okay. I can rewrite this as kinetic energy equals half I com omega squared plus half mr squared omega squared. Knowing in advance that v com equals omega r, and I have here omega r squared, so omega squared r squared, I can rewrite this as mv com squared. And now we have something new. Okay, something new, but also something old, if you wish. Okay, we have the rotational energy, half I omega squared, and we have the translational energy, which we know from before, half mv squared. Okay, and then this is a wheel, so you can think of it as not a disk. I would think of it as a hollow disk, just something like this, or actually not even this, no, just this. Okay, you can think of it as a donut, but with a very, very thin wall, or approximately here, if you actually take a look, the empty area is way more than the filled up area, so just a hoop. Yeah. Okay, and I'm using this because it has the simplest icon, mr squared. Okay, so it's easy to give examples with it. So we can say that a rolling object has two types of kinetic energy, and this is actually common sense. It has a rotational kinetic energy because it's rotating, and it has a translational kinetic energy because it has a velocity and it's moving at something, at some velocity. Okay, now the formal way to say this is it has two kinetic energies, rotational due to its rotation about its center of mass, and translation due to translation of its center of mass. This is the formal way of writing it down in words. Now, what about the forces? What sort of forces are we looking at? Well, let's look at something that's rolling. Okay, now these two are very different. Okay, look at them again. The first one, it keeps on rotating and moving, but something happens in the second one that doesn't happen with the first one. It drifts. Okay, it slips. It starts rotating, rolling, but at one point it stops rolling and it just starts sliding. Okay. Now the physics of these two are quite different. When sliding is involved, we have to alter our mechanisms a little bit. So let's take a look at both of them. Okay. Let's take a look at a wheel. It has a frictional force with respect to point P, and it's static friction, okay, because point P does not actually slide, right? So it's not kinetic friction, it's static friction, Fs. Okay, if it's moving, we can also use Fk. Just bear in mind it's friction for the time being. Acceleration of the center of mass is alpha r in a smooth rolling motion. Now, whenever you see a problem, whether it's in the book examples, whether in the other book examples, whether it's in the homeworks, whether it's in the tutorials, you will notice that almost 9 out of 10 times or 95 out of 100 times, okay, we will say something like there is no sliding, or it's in a smooth rolling motion, or there is no slipping. And the idea is we are looking at the top case, not the bottom case. Okay. Let's take the case of a ball or a disc rolling down a ramp. Okay. Now we have done this before with just a cube or an object that is sliding down the ramp. Now it's going to be different. It's going to be rotating and falling at the same time. It's a rolling motion. Let's write down our information. We have angle theta, this is P, we have our force, kinetic, the friction force in that way. We have gravity going downwards. We have our normal force going upwards. And you might wonder, why on earth is my normal force coming from the center, not from this point? Remember that when this is a diagram, when we're actually doing our free body diagram, we're going to be looking at everything through the center of mass. We have Fg sine theta, Fg cosine theta, Fg sine theta, a radius r. And my direction of motion is that way. So far, so good. Take a minute, absorb this, because we're going to be working on it in the next 2 slides. I've redrawn it here, but it's a bit smaller. Now, in the x-axis, in the y-axis, my net force is y. It's not floating up. It's not going through. F net is y. F net y is 0. In the x-axis, though, it is moving. It is accelerating. So F net equals ma in the x-axis. Let's start writing a bit more. What is our net F net due to? Well, I will take this direction to be positive and this direction to be negative. So I will put my friction as positive, Fs minus mg sine theta equals ma. Which a do I use? The center of mass in the x-axis. Now I also have torque here. My torque is going to be I alpha. Remember? F equals ma, torque equals I alpha. Okay. Torque is also RF. And my only force that is acting at this point is friction. So my R is my radius, capital R. And my force is friction. Now we have two more forces that we can consider for our torque. Okay. But it turns out they have zero moment arms. Fg and Fn both go through the center of mass, which means their R is exactly 0. Okay? So although there is a force, Fg cosine theta, but since it's going through the center of mass, my moment arm is 0. So it doesn't really apply on torque. Okay? So if I want to write the whole thing, I will say torque equals RF, which is equal to R gravity, F gravity, plus R friction, F friction, plus R normal force, F normal force. Okay. So given that point P is the point where the rotation is happening, so that's the center of rotation. Yeah. So bear in mind, center of rotation is point P, but center of mass is this point. Center of rotation and center of mass are not the same at this in this problem. Okay. Now when we do torque, okay, we do it around center of rotation, not center of mass. Or center of mass, not center of rotation. Which one do we do it at? Rotation, okay. Mass. The answer is, if you remember in our previous lecture, we worked it out. Okay, it doesn't matter where do you take it at, as long as you fix it. Okay, so here your fixed point is P, but your rotation is actually about what? Where's your center of rotation? Your center of rotation here is here at this point. P is simply the contact point, not your center of rotation. Okay? So, let's do it. We know we have Fg, but what is the distance between Fg and your center of rotation? They are both at this point. So you have your moment arm is 0. And this is the exact same thing with the normal force. So 0 Fn. Your only force left is this, because you have this distance between them. Okay. All right. So my torque is RFS, which is equal to I, alpha Okay, I can see there is a confusion. Let me try and alleviate that confusion. circle. Forget that this is a thick disk, okay? Just imagine of it as a circle. Okay. Now, when I am rotating it, if I'm rotating it here on my arm, okay, take a look. I am rotating it on my arm. Okay. What is the center of rotation? What is the center of rotation here? My center of rotation is the center point, right? The middle of the circle, the center of mass. Yeah? So, it is rotating about the center of mass this way, but the point which is in contact with my arm is not the center of rotation. It is this bottom point, right? So there is this distance, this radius between the contact point and the center of rotation. Okay. So when we are trying to, let's switch to a whiteboard. Let's do a free body force diagram. If this is my center of motion, okay, my normal force is going to be this way. My mg is going to be this way. If now I want to draw the friction, where is it going to be? Where is my friction going to be? I'll give you options. Option 1. Option 2. Okay. Or option 3, other. Excellent. Most of you chose other. Why? Because my friction can only happen in places where there is contact, right? I do not have contact with my center of mass. N and mg are with my center of mass, but I do not have contact with my center of mass. Okay? Friction is between the object and of the surface. So if I am now drawing my object, okay, this way, then my friction is going to be at this point, right? So my rotation is here in the center, but my friction point is at the contact point, which is not at the center. Okay. And I am assuming this thing is going in this way. So that's why friction is in the opposite direction. Okay. So now when I want to look at torque, torque equals R cross F. Okay. I need to do it about center of rotation. This is my center of rotation. Okay. Now, since mg and n both act at the center of mass, which is also the center of rotation, okay, your R is 0. But FR, you have this extra space, which is your radius of your circle. So your torque is going to be only equal to R cross friction. Okay. Mariam, I'm talking about the same thing in the PowerPoint presentation about this slopey thingy. Okay, but I'm taking away the slope and everything so that it's a very clear free body diagram without all the complications. Let's start again. F net equals MA. F minus mg sine theta equals MA. Torque equals I alpha. Torque equals R cross F. In this case, it's only RFS. So I will substitute that. RFS equals ICOM alpha. ACOM equals alpha R, which means alpha equals ACOM over R. Now, I will substitute that back in, and sorry. Okay. All right. So, where was I? Okay. I will substitute alpha equals ACOM over R. So, FS, ICOM, alpha equals A over R. I will bring this R also down, and I end up with FS equals minus ICOM, ACOM over R squared. وين راحت الام جي ساين ثيتا؟ الام جي ساين ثيتا موجوده داخل الايكوم. Okay, remember I'm only saying ACOM here, so ACOM involves all of this, but in the torque there is no mg sine theta. Okay, I end up with ACOM equals minus g sine theta 1 plus ICOM over mr squared. I'll do it one more time so that we get it. Okay, minus because the direction of the movement, it's clockwise, so minus. Okay, Mariam, it depends. If there is another force at anywhere but the center of mass, but the center of mass, which is also here center of friction, center of rotation, we take it. But in this example, we only have one force, which is not at the center of rotation, which is friction. Okay. Let me do it one last time. These are our three main equations. Okay. This will give me ACOM equals FS minus mg sine theta divided by m. RFS equals ICOM alpha, which is the same as ICOM ACOM over R. I will keep FS alone. Okay, it will be ICOM ACOM over R squared. We'll keep ICOM here. Okay. I'll keep ICOM here. And for ACOM, I will bring this back in. So ICOM over R squared, Fs minus mg, sine theta all over m. I have Fs here, and I have Fs on this side as well. Not a very good idea. I need to get Fs on one side since I'm trying to find what Fs is. Yes? Do we agree on this so far? What is Fs? Fs is mu n, which is mu mg cosine theta. Okay. Put it back in. Mu mg cosine theta minus mg sine theta divided by m divided by m. What is ICOM? It's mr squared or something else. Let's leave it for the time being. I get ICOM mu mg cosine theta minus ICOM mg sine theta divided by mr squared. And I can then, instead of wasting time, this, when I simplify it, will end up somehow like this. I know this is very complicated, so let's do it with numbers for a simpler example, and then we can come back to this. Okay? I'll do a much simpler problem. Let's take a very, very simple example. A uniform ball of mass m, 6 kilograms, and radius r, rolls smoothly from rest down a ramp at angle 30 degrees. The ball descends a vertical height 1.2 meters to reach the bottom of the ramp. What is its speed at the bottom? Let's build up. Okay, sorry, my bad. I started with a really complicated example. This is our problem. Angle 30 degrees, height 1.2 meters. We don't know what our friction is. Okay. We don't know what our VCOM at the end is. We need to find it out. Okay. Kinetic plus potential energy at the beginning equals kinetic plus potential energy at the end. Let's put it back in. At the beginning, we have potential energy, mgh, since it's at the top. We don't have any kinetic energy. At the end, we don't have any potential energy, but we have the total kinetic energy of both rotation and translation. So far, so good? Are we following? Good. Now, if I take this and simplify it, what do I end up with? Now, since this is a ball, since this is a ball, okay, we can take some data from our data sheet. Okay. The ball rolls smoothly, so there's no sliding. Okay. That says we can use V equals R omega. So we can use V equals R omega. Okay. What is our com for a ball? Sorry, what is our I for a ball? I com. 2/5 mr squared. Yes? I'll come to this, Noor. I'm doing it from the scratch. Okay. In the slide, I skipped some steps. Okay. This is for a ball. No sliding. Only rotation. So I have half I omega squared plus half mv squared equals mgh. 2/5 because it's a ball. If you go back to chapter 10, when we introduced the concept of center of mass and inertia in beginning of chapter 11, we gave a list. Balls are 2/5 mr squared. So half I omega squared plus half m r squared omega squared. I just substituted v with this. Okay. Equals mgh. Now I will substitute in icom. So I get half 2/5 omega squared plus half m r squared omega squared equals mgh. R squared. Where did I miss the r, the square? Half 2/5 mr squared. Simplifying time, m goes away. 2 and 2 go away. We end up with omega r squared over 5, omega squared r squared over 5, plus omega squared r squared over 2 equals gh. Half plus 1/5 is 7/10. Omega squared r squared. Is equal to GH. And now اسمه حسن. Okay. I will put in back V equals R omega. So 7/10 V com squared equals GH. V com equals 10/7 GH all square rooted. Do we follow what we just did to find what our V com is? Okay. We have done a very obvious case of وين أذنك يا جحا. We started with something simple. We made it way more complicated. Then we simplified it back again. Okay. All right. Okay. Yes, Ayham. هذا ما في friction. We'll come back to the friction. And I noticed. Okay. I'll share the entire whiteboard, Mariam, because there's quite a bit today. Okay. I noticed that I started with something with friction, which is complicated. So it causes a lot of headache. So what we're going to do is we're going to make it. I start with something simpler, no friction, and then I'm going to build up to friction again. Okay. Okay. Now, that we have done that, okay, let's look at part B. What are the magnitude and direction of the frictional force on the ball as it rolls down the ramp? I lost my connection for a minute, I think. Can you see me?
Yes.
Okay. Now let's go on to the next bit. Okay. What are the magnitude and direction of the frictional force on the ball as it rolls down the ramp? Because the ball, okay, rolls smoothly, okay, we can use 11-9. Okay, there is no simpler way to do this. Let's see if your book does it in a simpler way. Nope. Okay, let's find another way to do this. We cannot move on until we have explained this part properly. Okay, I figured out a simpler way to explain it. Let me just copy paste everything to the whiteboard. Okay. Okay, so without friction, we're all happy, right? So far? Yes? Okay. With friction, okay, I'll put this to a side and I'll do it all over again. Okay. F equals ma. I chose this direction to be positive, this direction to be negative, right? Good. Fs minus mg sine theta equals ma. I also said torque equals I alpha, which is equal to I. No, let's keep it this way. Okay. We said A equals alpha R. Yes, no? Yes. Okay. Mariam, that is possible. You can do that, which is what I tried to do before, but then I end up with something even more complicated with cosines and sines, and it's going to confuse you even more. But yes, we can do that. Okay, it is possible. Okay, all right. Now, I will keep it Fs. Nope. R Fs equals I com alpha. Now here's a question. Alpha is equal to A over R, صح? What is the direction of my A? In which direction is it accelerating? Up or down? Down, right? And what did I say down is? I defined down to be minus. So now when I am substituting alpha, okay, I need this A to be also minus because it's going downwards. Okay. So I end up with minus I A over R RFS. Now, if I just put Fs alone, I get minus IA over R squared. We still didn't get the 1 plus. Now, I need to substitute the A. ما عندي حل. Fs equals minus I over R squared. I'll take it out. But my A is, from this, my A is Fs minus mg sine theta divided by m. Now I have Fs here and Fs here. And since I want to find what my friction is, this is not very useful. I need them all on one side. Okay, so I have no option but to write it this way. Fs equals minus I Fs over mr squared, minus minus is plus, plus mg sine theta divided by, oops, sorry, I forgot the I, minus I mg, plus I mg sine theta mr squared. Yes, Waad? Let me put all the Fs's on one side. Fs plus IFS over mr squared equals IMG sine theta over mr squared. السالب تبع A ما تروح مع سالب torque. Well, torque is equal to R cross F, صح؟ نحن بعدنا ما حددنا what is R cross F. Okay, it might be positive, so it might not go plus and minus. Remember, omega negative and omega positive, that is for angular velocity. Torque is you'd use the right-hand rule, so it might be up or down even. Okay, so we don't know if the torque is positive or negative yet. Okay. Actually, if you want to even be more pedantic about it, since it's rotating this way, okay, without calculations, you can say it's positive. Yeah? Since it's going this way, the entire body is going counterclockwise. We can say torque is alpha is positive. Torque is positive. Okay. All right. So mr squared plus IFS over mr squared equals IMG sine theta over mr squared. Simplify. Mr squared plus IFS equals IMG sine theta IFS equals
دكتور
أيوة.
الفريكشن فورس مال أول شيء وين راحت؟ ليش ما نزلناها؟
وين friction force مال أول شيء؟ Oh, it should be still here.
أيوة.
نسيتها. Okay. نطلع الفريكشن فورس FS 1 sorry I plus MR squared صح؟ IFS plus I plus FS MR squared. FS equals IMG sine theta تقسيم I plus MR squared
دكتور
اها
شوية لو سمحت طلع فوق، أريد أقول شيء.
أيوة.
ليش هنا من البداية ما خذينا الفاكتور اللي هو الفريكشن فورس قبل أن توحد، يعني قبل أن تحذف، قبل أن أصلا توحد المقامات في هذا الطرف، بناخذ الفريكشن فورس تبقى لنا 1 بلس الآي، بعدين عاد نقسم فبيكون نفس اللي موجود عندنا هناك، يعني ما نوحد وكذا.
وين؟
دكتور شوف هذا اللي بالأسود أول شيء.
هذا؟
أيوة. إنزين
أوكي.
ليش من البداية ما خذينا الفريكشن فورس اللي هي عامل مشترك؟ يبقى لنا ال1 بلس الاي اوفر ام ار سكوير.
FS 1 plus I over MR squared. حلو.
بعدين
equals IMG sin theta على MR squared. حلو. بعدين
نقسم.
بهذه الطريقة؟
أيوة.
ممتاز. هل وصلنا لهذه النقطة؟ Okay. You can do it either way. So you can do it this, or you can write it down using this way. Okay. And if you want A, you can reshuffle it to get A as the subject. Is everyone okay with this? This was one hell of a headache. Let's move on, since everyone's okay with this. Yes, the minus depends on the direction. Because we chose this to be minus, we ended up with a minus. If we had done the exact same problem, but said, you know what, this is minus and this is plus, we would have ended up with a plus. Okay. Let's hope after all this, we have actually gotten the concept. Let's do a very, very simple concept test. Why do we want both F and A? okay, we get F in terms of A and A in terms of F. Look. We get F in terms of A, or we can rearrange to get A and substitute what F is to get this. Okay? Right. A hollow cylinder of mass m and radius r rolls down an inclined plane. A block of mass m slides down an identical inclined plane. Complete the following statement. If both objects are released at the same time, which one will reach the bottom first? Cylinder, block. Block will reach the bottom with greater kinetic energy. Cylinder will reach the bottom with greater kinetic energy, or they will reach at the same time. No calculations, just think about it. Your potential energy is being divided how many ways? Okay. What if I tell you the correct answer is this? Think of it this way. You start at the top, you have MGH, صح? You have block, you have cylinder. Okay. How will this MGH be distributed? Here, it will all go to half mv squared. Here, it will go to half mv squared plus half I omega squared. But the total energy is still the same, MGH. So if you started here with 100, here all of the 100 will go to this. Here, the 100 is going to be split between rotation and translation, which means, by definition, okay, my velocity of my cylinder will be less than that of the block, since some of the energy is going to rotation. Right? So the block will reach the bottom first because it has a higher velocity. We cannot say with greater kinetic energy. Why? Because the total kinetic energy here is equal to 100, and the total kinetic energy here is equal to 100. Rayan, that's because it's a block. There's no radius, it's a rectangle. Okay. Let's try it. Vcom for a sphere is 10 over square root 10 over 7 GH. And for a block, okay, it will be half mv squared equals mgh. The m's go away. Okay, your v squared is equal to 2gh squared. Which one is bigger? Block is bigger. 2gh is more than 10 over 7 gh. Yeah. Think of it this way, without going into all the equations, yeah? Think of it this way. You have 100 riyals, okay? Okay. You either give it to one person or more than one person. It doesn't matter how many more than one person it is, or you know how big the one person is. Okay, if you give it to one person, that one person gets the full 100 riyals. Yeah. If you give it to more than one person, then you end up splitting it between more than one person. Okay. Forget the equations. Just think of it in terms of money. We all love money. Okay. Someone is giving you 100 riyals or giving you and someone else 100 riyals. Which one do you pick? You want it all for yourself, right? Because you get the full amount. Exactly the same here. Okay. Here's a nice homework problem. Try to do it on your own. Remember, this is for a sphere, not a cylinder. So I might be wrong. Try it for a cylinder, and at the beginning of next lecture, tell me if you can prove this wrong or right. Okay? Tell me if you can prove that I am wrong and that the cylinder needs to reach first. Yes, same M. Wad. Notice, M does not play a part in either equation. Okay. Consider the following three objects, each of the same mass and radius. So same M, same R. A solid sphere, a solid disk, a hoop. Okay. All three are released from rest at the top of an inclined plane. The three objects proceed down the incline, undergoing rolling motion without slipping. In which order do the objects reach the bottom of the incline? Can you still see the question? So the correct answer is 1, 2, 3. Why? I sphere equals 2/5 mr squared. I disk equals mr squared. I hoop, did I get this right? Cylinder is half, sorry, this is half mr squared. And I hoop is equal to mr squared. Remember, your energy goes to half mv squared plus half I omega squared. So the smaller the I, the more, the less this is, and the more your velocity is. Right? So you end up with an order. This is smallest, second smallest, third smallest. مريم هذول من الجدول عملناهم last time, 2 lectures ago actually, in center of mass. Where is it? Moment of inertia and rotational kinetic energy. We have a whole, here we go. It's in your book. It was also in the lecture theaters. Mariam, this chapter is a little bit unusual in that we don't usually translation is something that we do on a regular basis, day in and day out. Okay, but rotation is not something that we think of on a regular basis. Okay, so it's a little bit more complicated. Okay, I think this is enough for today. I really wanted to introduce angular momentum, but we don't have enough time, and there's no point introducing half of it. Okay, so we can do this later on. Okay, let's see if we have questions. Quiz is 9.5 plus chapter 10. So this chapter is not involved. Chapter 10 is not involved as per the work plan. 9.6 is not included on its own, but the concept of center of mass is included in chapter 10. Okay. Let's see. Yes, all of chapter 10. It's one chapter only. ريان كان المفروض انه ما في محاضرات, but because we lost 3 or 4 lectures in between, week 15 we will have lectures in week 15. Okay, I managed to remove one chapter of the course. Chapter 15 we have removed it. Okay, but I cannot just stop at chapter 10 or chapter 11. It's not possible. Okay. One at a time. Yes, Mariam, what's your question?